Gas giants play an important role in the equilibrium of our system. Their gravity extends so far that it affects the movement of the inner planets, while tidal forces hold dozens of satellites captive. Today, we'll take an amazing journey around the outer solar system. We'll start out near Saturn's great, mesmerizing rings. We will pass by the mysterious Enceladus and its majestic geysers, and then approach Titan, lying hidden beneath a thick, opaque atmosphere. Next, our flight will take us to Jupiter and its fantastic satellites. And then, we'll plunge into a vast region of instability called the main asteroid belt. The laws reigning here are barely comprehensible to us, but chaos theory will help us unravel them. Let's get ready, and we begin. Saturn's rings do not have a clear-cut border. The width of their visible part is about as much as 280,000 kilometers, although there are thinnest clusters of dust and rarefied gas beyond these borders. These structures' diameter reaches 16 million kilometers, according to some estimates, although they cannot be seen from the Earth on account of their extremely low density. In spite of the impressive dimensions, the total mass of the ring system is quite small by space standards and is estimated at 3 times 10 to the power of 19 kilograms, which is about 2,000 times lighter than the Moon. Solid objects account for only 3% or so of the structure's overall volume, with the rest filled with rarefied gas and cosmic dust. The disk surrounding Saturn is conventionally divided into several large rings. However, a rather powerful optical telescope will reveal each of them to be clearly made up of a large number of thin circles separated by narrow gaps. These gaps form due to the gravitational influence of both the planet itself and its many satellites. Some of them are as much as several hundred kilometers wide. Even though Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are next to impossible to see. For example, the D ring, the closest to the planet, which consists of tiniest water ice crystals and frozen methane. Its upper border is posited to be located 16,500 kilometers above the planet's conventional surface. As for its inner part, the ring has no clear-cut border and gradually fuses with Saturn's atmosphere. Next to it is the brighter and more massive C ring, which is approximately 17,500 kilometers wide. It is comprised of space objects measuring up to 2 meters and which make up just 0.033% of the disk's overall mass. The brightest and most outstanding part of the disk is located further and is designated the B ring. It begins roughly 34,000 kilometers above the surface of the gas giant, and its width reaches 25,000 kilometers. The thickness of the larger part of the ring does not measure over 5 to 10 meters, while its outer part forms a vertical rim towering up to 2.5 kilometers high. The outermost visible ring of Saturn begins 64,000 kilometers above the planet's surface. It is roughly 14,600 kilometers wide, harboring not only comparatively large ice bits of 10 meters and more, but some satellites as well, such as Pan, Daphnis and others. The existence of such large objects may prove the theory of ring formation following the destruction of the ice satellite. Alternatively, they may have formed at a later time as a result of smaller fragments colliding and merging. Beyond this part of the disk, there lie the almost unobservable F, G and D rings, which formed from cosmic dust and rarefied gas. It goes without saying that most of Saturn's large satellites actively interact with the rings. Traveling as far as 179,000 kilometers away to the region of the so-called E ring, the celestial body dubbed Enceladus is to be found. With a diameter measuring just 500 kilometers, it does not qualify as one of the gas giant's largest satellites, but it stands out for other reasons. The point is that Enceladus is one of the few celestial bodies in our system where there are clear manifestations of cryovolcanic activity. Analysis of the observed emissions proves that there is an ocean of liquid water under its surface. Mathematical modeling shows that its temperature measures from 45 degrees Celsius below zero in the upper layers to 0 degrees at the bottom. Due to a high content of dissolved salts and ammonia, the ocean does not freeze over even in sub-zero temperatures, with the icy shield about 2 kilometers thick covering and thermally insulating it. The celestial body's surface temperature is about 75 Kelvin or 198 degrees Celsius below zero. Its atmosphere is extremely rarefied and is 91% water vapor. Other elements making it up are nitrogen, carbon dioxide and methane. Powerful geysers that erupt from time to time through cracks in the icy crust of the satellite regularly supply its atmosphere with chemical elements, but the celestial body's weak gravity is not enough to prevent the atmosphere from floating away. The upper region of the atmosphere is constantly losing some amount of particles that go to sustain the E-ring. On the other hand, Enceladus constantly captures material from the space around it, thus ensuring its peculiar chemical balance. It is known that geyser activity of this celestial object depends on its orbital movement. It is likely that Saturn's tidal forces deform the satellite's icy shield, causing it to crack in multiple places and to erupt. It is also known that the cryogeyser's emissions contain elaborate organic molecules, which may mean that the conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Also, the gas giant's fifth largest and most massive satellite, Tethys, can be seen approximately 300,000 kilometers away from it. It is peculiar for sharing the same orbit with two other celestial objects, Telesto and Calypso. They are located at the so-called stable Lagrange points, with Telesto 60 degrees ahead of the main satellite in its movement along the orbit, while Calypso, on the contrary, lags 60 degrees behind. Unlike the massive spherical Tethys, these celestial bodies are not that large and are irregular in shape. They measure roughly 20 to 30 kilometers in diameter, with their overall mass just several trillion tons, which is modest by space standards. Interestingly, modeling shows that Calypso and Telesto could not have originally formed in the same orbit with a more massive body following it, which means that they arrived to join it at a much later time. As for Tethys, it is a celestial object with a diameter measuring about 1,060 kilometers, made up of mostly water ice, with some rocky impurities in its composition. The most outstanding feature of its relief is the giant impact crater Odysseus. Its diameter measures around 450 kilometers, which is about twice as small as the diameter of Tethys itself. Its depth reaches as far down as 3 kilometers. There is also an easily noticeable chasm of enormous proportions on the satellite's surface, which is called the Ithaca Chasma. It is as long as about 2,000 kilometers. That is about a third of the celestial body's circumference and as much as 100 kilometers wide. As for its depth, it ranges from 3,000 to 5,000 meters, and the bottom is pockmarked with a great number of craters and minor irregularities of the surface. According to one of the theories about it, the Ithaca chasm formed as a result of Tethys's subsurface ocean freezing over. On turning into ice, the water expanded in size and erupted through the satellite's outer crust. Another assumption about the chasm has to do with the Odysseus crater. It is thought that the impact waves traveled across the entire surface of the satellite and caused a powerful resonance around its circumference. As a result, Tethys's crust cracked, forming this incredibly large chasm. Still further from Saturn, there lies its largest satellite, Titan, which also boasts quite a number of highly unusual features. With a diameter measuring 5,152 kilometers, it is in fact the second largest satellite in the solar system, with Ganymede holding the first place. It is also remarkable for being 5.5% bigger than Mercury. Titan is also the only satellite in the solar system with a dense atmosphere and bodies of liquid on its surface. Since Titan lies quite far from the Sun, the temperature of this celestial body is quite low at around 94 Kelvin or 180 degrees Celsius below zero. Having said that, in spite of its comparatively small mass, Titan is capable of sustaining an atmosphere which is 1.5 times denser than that of the Earth. Nitrogen accounts for over 98% of the atmosphere's chemical composition, with methane and other gases making up the rest. Exposed to solar wind, nitrogen and hydrocarbon compounds in the atmosphere's upper layers transform into more complex organic substances, which subsequently slowly settle on Titan's surface. Due to the impermeable hydrocarbon smog, the satellite's surface is unobservable in the optical range. According to the most plausible model of Titan's inner structure, there is a massive rocky core at its center, with a diameter measuring about 3,400 kilometers. It is embedded in a thick layer of exceptionally dense ice, which forms the bottom of a cool salty ocean containing up to 10% of dissolved ammonia. It is buried under a crust of water ice mixed with methane hydrate, which is many kilometers thick. In temperatures as low as that, the ice has properties identical to those of a solid substance and forms mountain ridges and elevations on the surface. As for lowlands and chasms, they are filled with lakes of liquid ethane and other hydrocarbons. Solar wind and Saturn's extremely powerful magnetic field constantly strip Titan of its atmosphere. However, its internal processes keep replenishing it, so the process of losing it may take billions upon billions of years. When the Sun hits the red giant phase, it will be capable of vaporizing the hydrocarbon haze and melt the eternal ices on Titan. After this, the satellite will become a more favorable place for the genesis of life. However, it will not happen for a while yet. Of course, Saturn's system does not end there. Titan is located about 10 astronomical units from the Sun and is outside the habitable zone of our star. It is Saturn's largest satellite, and its orbit lies well outside the Great Rings, at a distance of about 1,200,000 kilometers from the center of the planet. The trajectory of the celestial body is close to circular, and a complete orbit around the gas giant takes a little less than 16 Earth days. Titan's diameter is 5,152 kilometers, which is 5.6% larger than that of Mercury. At the same time, the mass of the celestial body is relatively small at only 1.35 times 10 to the power of 23 kilograms, which is about 40% of Mercury's. Calculations show that the satellite's average density is about 3 times less than that of the Earth, which means it has a completely different chemical composition. According to contemporary concepts, Titan has a massive core at its center, about 3,400 kilometers in diameter and made up of various silicon compounds. It is surrounded by a thick layer of densely packed ice, which is at the bottom of a cold liquid ocean hundreds of kilometers deep. The ocean, in its turn, contains large amounts of dissolved ammonia, methane and various caustic salts, so that its freezing point is markedly lower than that of ordinary water. For this reason, Titan's subsurface ocean remains liquid even in sub-zero temperatures. It is bound by a thick crust around 100 kilometers thick, consisting of a mixture of water ice and methane hydrate. The tidal forces of the nearby Saturn are continuously deforming it, causing massive rifts and fractures. This causes large cryovolcanoes to form, ejecting great quantities of methane, ammonia and water onto the surface of the celestial body. Methane plays about the same role in Titan's atmosphere as water vapor on Earth. The fact is that the average surface temperature of the satellite is only about 94 Kelvin or 179 degrees Celsius below zero, which is slightly below its boiling point. Natural variations in this parameter cause hydrocarbon vapors to condense and precipitate, forming methane seas, lakes and rivers. Titan's atmosphere is composed mainly of hydrogen, which makes up about 98.4% of its volume, while methane accounts for about 1.6%. Due to its extremely low temperature, the satellite's atmosphere remains condensed near its surface, and the ring of the mountains surrounding it is less than 500 meters high. Most of the surface of the celestial body is permanently obscured from our eyes by multi-layered clouds and an orange-yellow Tholin haze. This unique weather phenomenon is a fog formed by tiny droplets of liquid methane and dissolved organic matter, which gives Titan its characteristic hue. This haze pervades Titan's surface, absorbing and scattering visible light but transmitting infrared light. This peculiarity leads to an unusual anti-greenhouse effect, which cools the satellite's surface by roughly another 10 degrees. This effect makes Titan difficult to explore, but thanks to the Cassini's orbiter's infrared cameras, Titan was in parts mapped out earlier this century. Of course, it is not as accurate as we would prefer, but even this much is enough to outline the most striking features of the celestial body's surface. The face of Saturn's largest moon is full of contrasting spots. Some of these reflect most of the light that falls on them, while others are relatively dark in color. One such area is slightly south of the equator and is called Aztlan. One of Titan's highest mountains, Mount Doom or Doom Mons, is located here, towering about 1.5 kilometers above the surrounding plains. The whole mountain reaches up to 60 kilometers in diameter. Its summits are craters, and its slopes have relatively fresh traces of turbulent flows. This may suggest that Doom Mons is an active cryovolcano. To the northeast from it is Titan's deepest depression, called Sotra-Patra. It is a giant depression about 30 kilometers long, the bottom of which is located about 2 kilometers below the adjacent plains. It is thought to be the mouth of a huge cryovolcano, and is part of a single tectonic structure along with Doom Mons located close by. To the north of Doom Mons, there stretches the immense Mahini Fluctus, a vast area covered by Doom Mons' ejections. The area extends for about 180 kilometers and varies in width from 15 kilometers in the south to 60 kilometers in the north, where torrents of frozen material alternate with expansive fields of sand dunes consisting of a mixture of frozen methane and water ice. Our flight will continue over the dark area of Fensel. The largest impact crater of the celestial body, Minerva, is located in its northwestern part. It reaches 440 kilometers in diameter, which is about 3 times larger than any other crater on Titan. The depression is about 200 meters deep, and the ring of the mountains surrounding it is less than 500 meters high. The fact is that according to studies, Minerva is not only the largest, but also the oldest extant crater on Titan. Different estimates put the age of the crater at between 300 million and 1.2 billion years. Erosion and tectonic processes have severely damaged the crater, and it is only thanks to its sheer size that it is still visible. Minerva has a well-defined internal structure. At its center there is a small flat plain, surrounded by a ring of hills. This region, with a total diameter of about 200 kilometers, is rather light and clearly visible from space. It is surrounded by a so-called moat, a stretch of dark plains about 50 kilometers wide. This is followed by a ring of low mountains that form the outer boundary of the crater. Our flight next takes us to the south. Here is one of Titan's most impressive and mysterious landmarks, Hautei Arcus. This is a unique formation in the solar system. It is a bright, arc-shaped region about 600 kilometers long. Radar data from Cassini shows that Hautei Arcus is a natural boundary between the Rocky Mountains in the northeast and a wide valley in the northwest. It is also noteworthy that some parts of this area change color from time to time. This phenomenon is thought to be linked to the eruptions of cryovolcanoes, whose emissions cover the surface of the satellite in a thin layer and then flow into a nearby valley or evaporate into the atmosphere. From space, one can clearly see light channels similar to riverbeds running from the mountains of the Hautei Regio to the northwest. This is where Xanadu is located, which is a vast lowland area with highly rugged terrain. Its northwest boundary is formed by Mithrim Montes, which are 3 parallel ridges stretching for about 150 kilometers, with an average height of 1.9 kilometers. Among the peaks of the southern range is the highest peak on Titan, reaching 3,337 meters. Standing on top of it and looking west, you can see a vast dark plain stretching several hundred kilometers in front of you. It is called Shangri-La, and it is thought that this whole area used to be flooded with liquid methane. It is assumed that it may have persisted beneath the topsoil, similar to the Earth's underground water. Most of this region is below average elevation and has a comparatively flat terrain, but lighter hills can be seen in some places. In the past, these may have been islands in the middle of a hydrocarbon sea. To the west of Shangri-La is the bright Adiri upland area, clearly visible against dark regions around it. The area extends for up to 2,500 kilometers and is a veritable network of numerous drainage canals and caves clearly visible in the photographs. These are thought to have been formed by abundant flows of liquid hydrocarbons. To the west of Adiri is the vast dark lowland area of Belet, and to the east, near the border with Shangri-La, is the Huygens landing site, so far the only vehicle that got to touch down on the surface of an object in the outer solar system. The descent probe was part of a science program called Cassini-Huygens. Together with the Cassini automatic probe, it left Earth in 1997 to spend 7 years in interplanetary space. The spacecraft entered the orbit of Saturn only in 2004, and in early 2005, Huygens reached Titan and plunged into its atmosphere towards new discoveries. Cassini, on the other hand, remained in orbit around the gas giant to carry out its part of the research program, as well as to continue serving as a transponder for the lander. The probe spent just under 2.5 hours in the atmosphere, gradually dropping speed using a sophisticated parachute system. Eventually, by the time it touched down on the surface, its speed was 4.4 meters per second. The probe successfully withstood a momentary 15-fold overload and soon went on to collect information. Huygens was equipped with a vast array of scientific instruments, most of which were designed to study different aspects of the satellite's atmosphere. The probe used them to measure the strength and direction of air currents, as well as the electrical conductivity, temperature, and composition of the atmosphere. The probe also took photographs and made audio recordings, and on landing, it examined the composition and properties of the ground. The first thing the cameras saw after making contact with the surface was a flat plain, dotted with rounded rocks of various sizes, the shape of which clearly indicated the impact of powerful fluid currents. A special drill was also used to sample the surface, penetrating 15 centimeters into the ground, while multiple sensors measured its density, texture, and composition. It turned out that a thin layer of small rounded pebbles lay on a relatively soft but dense substrate, similar in consistency to wet sand or dense snow. Also, methane gas was released during the drilling process. The ground at the Huygens landing site is believed to have been like sea sand, saturated with liquid hydrocarbons. In total, the probe transmitted around 500 megabytes of information to Earth, including 350 photographs. Further careful analysis revealed several unique features of the celestial body related to its atmosphere. For example, it turned out that at an altitude of about 80 kilometers there is a layer of almost complete calm, as if separating Titan's atmosphere into two parts. Neither air currents of the upper atmosphere nor winds of the surface reach this layer. What caused this phenomenon is not yet known. Another feature is that Titan has two ionospheres. The first of these is located at an altitude of about 1,200 kilometers. It is a layer of heightened electrical conductivity with a large concentration of ionized particles. This layer is known to be formed by stellar wind streams and cosmic radiation. The second ionosphere lies much lower, at an altitude of about 60 kilometers, and the reason for its formation is still debatable. Moving northwest from the Adiri area, we reach Titan's largest hydrocarbon reservoir, the Kraken Mare. Its total area reaches 400,000 square kilometers, which is slightly smaller than the Black Sea. Due to the high viscosity of the liquid hydrocarbon mixture, it has not yet been possible to measure the exact depth of the reservoir. It is only known that in most of the area, it is over 200 meters. Another large natural basin, the Ligeia Mare, is located slightly to the north, near Titan's pole. Its diameter reaches 500 kilometers, and its area is about 100,000 square kilometers, which is about 3 times larger than Lake Baikal. The seas are connected to each other by the narrow and long Treves Fretum, 173 kilometers long. Also in the subpolar region, there are many smaller lakes and lagoons filled with liquid methane. In 2014, analysis of earlier images beamed back by Cassini revealed a large bright object on the surface of the Ligeia Mare. On comparing photographs taken at different times, it was established that within a few months the mysterious object had grown to 260 kilometers in diameter to disappear almost instantly without a trace. Several hypotheses have been put forward to explain it. According to one of them, temperature differences lead to a constant stirring of layers of liquid hydrocarbon mixture in the Ligeia Mare. This causes nitrogen bubbles to form and rise to the surface from the depths of the reservoir, and thus form large clusters of persistent shiny foam. Due to the high viscosity of the hydrocarbons, such bubbles can reach 4.5 centimeters in diameter and remain stable for months. From space, these structures resemble large islands because they reflect infrared radiation well. Such bubbles would have been a significant hindrance to the operation of a submersible probe, which was scheduled to be launched to Titan back in 2010. However, the mission was postponed indefinitely for various reasons. A higher priority was given to the Dragonfly program, which NASA is working on now. The vehicle is currently in the design phase and has just recently passed key tests of its blades. The launch from Earth is scheduled for 2027. As conceived by its creators, Dragonfly will be an octocopter, an aircraft with 4 twin propellers. This design will allow it to stay in the air even if it loses several blades, unlike its predecessor, the Ingenuity Mars helicopter. A radioisotope thermogenerator, powerful enough to enable the vehicle to climb to a height of 4 kilometers and travel at a speed of about 36 kilometers per hour, will be used as the power source. The scientific capabilities of the probe are also impressive. It will be equipped with a versatile camera capable of producing both panoramic photographs of the surrounding terrain and macro images of the ground. At the same time, the mass spectrometer will make it possible to determine the chemical composition of atmospheric samples and the internal structure of rocks. Perhaps Dragonfly's data will help us clarify an important question. Do we at least have a chance of encountering primitive life? The possibility of life on Titan remains hotly debated. On the one hand, the extremely low surface temperature, the presence of extremely toxic hydrocyanic acid in the atmosphere, and the absence of liquid water would likely rule out the presence of biological life as we know it. Titan's atmosphere, on the other hand, exhibits an incredible diversity of organic compounds. Nitrogenous bases and amino acids, which are the building blocks of proteins, RNA and DNA, could be naturally synthesized on its surface. It is also known that liquid methane can serve as a solvent and potentially play the role of water in biochemical reactions. In addition, experiments show that under certain conditions, a mixture of liquid hydrocarbons with phosphine forms an environment similar to the primordial soup of the early Earth. This means there's a chance of encountering downright exotic forms of life on the surface of the satellite. For biological life to originate and start evolving, a medley of a great number of factors is called for. The chief ones are liquid water, an energy source, and a certain chemical diversity. Apart from the Earth, several more places in the solar system are potential life-harboring candidates, with Mars as the most prospective one and most closely studied starting from the recent past. Still, there are chances of discovering alien life beyond its orbit too. All it takes is to have a closer look at the next closest planet to us after Mars if we look away from the Sun. Jupiter is the largest planet in the solar system. Its mass is 318 times that of the Earth. This is a gas giant made up mostly of hydrogen and helium. Apart from these, methane, ammonia, sulfur and nitrogen compounds and water ice have been detected in its atmosphere. In spite of the diversity of chemical compounds, the possibility of finding life forms on Jupiter itself is minuscule. What with the absence of any hard surface, high temperatures of the planet's inner layers and unimaginable pressure in its interior, biological creatures simply have no chances of survival. At the same time, Jupiter boasts quite a vast array of moons. 4 of the most well-known ones, Io, Callisto, Ganymede and Europa, were discovered as far back as in 1609 by Galileo Galilei. Quite close to the Moon and Mercury in size, they are on the list of the largest satellites in the solar system. It is also suggested that Jupiter accumulated substantial amounts of thermal energy due to gravitational contraction when forming. As a result, it is now giving off more of this energy than it is getting from the Sun. That is why the gas giant, with all the objects orbiting it, may be seen as a curious version of the solar system in miniature. At first glance, Jupiter's moons may appear to have no prospects in terms of searching for extraterrestrial life. Far from the Sun, they are encased in ice, and their atmospheres are not dense. However, on closer scrutiny, these celestial objects reveal something excitingly promising. Callisto, Europa and Ganymede are highly likely to have liquid oceans under the ice shell. Estimates show that space objects with concealed oceans may offer favorable conditions for life even if they are much further from their star than planets like our Earth are from the Sun. The thick icy shell on their surface serves not only as protection against radiation and meteorite infall, but also acts as fairly good thermal isolation. That is why it is feasible that conditions inside a massive layer of water may be good enough for life to originate and evolve there. These assumptions make Jupiter's satellites some of the most attractive objects for exploration within the solar system. And now let's have a closer look at each of them. Ganymede is the largest and most massive celestial object in Jupiter's environs. Of all the satellites in the solar system, it is not only the one sporting the most impressive dimensions, but it also resembles a real planet more than any other. Ganymede's radius measures 2,634 kilometers, which is 8% more than that of Mercury. As for its mass, it equals 1.48 times 10 to the power of 23 kilograms. This is twice the mass of our Moon. Interestingly, Ganymede is the only satellite in our solar system with a liquid metal core and its own magnetosphere. Processes of nuclear decay take place in Ganymede's interior. This heats the satellite still more, with the average surface temperature 110 Kelvin or 163 degrees Celsius below zero. The core, on the other hand, is estimated to be as hot as up to 1,500–700 Kelvin. Investigations of Ganymede's magnetic field carried out by the Galileo space probe showed that there may be a multi-layer salty ocean under the satellite's icy shell as deep down as 200 kilometers or more. The number of layers may reach 4. Water in each is of different salinity, density and temperature, with the layers separated from each other by some ice. Spectrographic investigations of Ganymede's surface show it to have a rather rarefied oxygen atmosphere. This, however, isn't an irrefutable proof of there being biological life on the satellite. Molecular oxygen is likely to form as a result of the exposure of water ice to ultraviolet radiation. Hydrogen, the other product of this chemical reaction, floats away into space. Oxygen, meanwhile, which is a heavier element, settles close to the surface. Apart from large amounts of water ice, other elements found on Ganymede's surface are carbon dioxide, sulfur dioxide, sulfates, and some other organic substances. They may well have originated in the depths of the subsurface ocean, but the mechanisms of their settling on the satellite's surface are still not clear. Callisto is another celestial object potentially just as attractive for life. This satellite is Jupiter's second largest one and lies furthest from it. Its diameter measures 4,820 kilometers, almost like that of Mercury. Callisto is encased in an icy shell as thick as 80 to 150 kilometers, and it is highly likely that there is a salty ocean concealed under it containing large amounts of ammonia and other substances. The estimates of its depth range from 50 to 300 kilometers, and its temperature is around 251 Kelvin or 21 degrees Celsius below zero according to most models. Due to impurities and high pressure, the water in the ocean should remain in its liquid state. Below the subsurface ocean there is bound to be a layer of ice as thick as around 300 kilometers, and the satellite's core, made up of water ice and rocks, lies still deeper down. Callisto's surface is pockmarked with craters. Spectral analysis of light reflected from this celestial object revealed not only water vapor and silicon rocks, but also ammonia, carbon dioxide, sulfur, iron and magnesium compounds, as well as tholins, complex organic polymers containing nitrogen. These brightly colored substances form on the surfaces of celestial bodies, a result produced by ultraviolet radiation. Callisto happens to lie too far from Jupiter to get more heat from it. Besides, the tidal influence exerted by the giant neighbor isn't enough to deform the satellite, although friction in the process would heat it up. Also, most of this body is made up of ice, whereas it is preferable that there should be solid rocks, which would saturate water with elements vital for life forms to originate. With the diversity of chemical compounds here rather modest and the temperature quite low, it hardly improves chances of life evolving here. Still, this possibility should of course not be ruled out yet. The most promising of Jupiter's satellites in terms of searching for alien life is Europa. The smallest of Jupiter's 4 Galilean moons, it is just a bit smaller than our Moon. The equatorial temperature on this celestial body is 110 Kelvin or 163 degrees Celsius below zero. At the poles, temperatures may drop to 50 Kelvin or 223 degrees Celsius below zero. Europa is tidally locked to Jupiter, facing it with the same side only. However, its rotation isn't synchronized ideally. there are deviations from the calculated trajectory. This may mean that there is a liquid layer between Europa's surface and core. This assumption is confirmed by observation of interaction between the satellite and Jupiter's magnetic field carried out by the Galileo space probe in the late 20th century. Apart from that, analysis of crevices Europa's surface is covered with shows that the satellite's crust moved 80 degrees with respect to the interior. This would have been impossible without a liquid layer between them. The massive neighbor exerts a strong influence over Europa by causing powerful tidal waves in its subsurface ocean. This way, the satellite is heated still more by internal friction. Estimates show that the temperature in Europa's interior is high enough for an ocean of water to be in liquid state. Its depth may reach 100 kilometers, and its volume may be twice that of the global ocean on our Earth. Europa is covered with an even layer of exceptionally smooth and clear ice. The highest elements of relief tower just several hundred meters above the surface. The thickness of the icy crust may be anything from 10 to 30 kilometers, although the satellite's surface is streaked with a whole net of long and deep cracks. Some of them may well reach as deep as the subsurface layer of water. Thus, the ice at the bottom of these ravines is valuable material for studying the inner makeup of Europa. Another peculiar feature of this moon is powerful ice-cold vapor geysers. They open up only when Europa is at its furthest point from Jupiter, with the height of the spurts reaching as much as 200 kilometers. These giant jets are made up of water vapor, which incidentally is unexpectedly clean. It is still not known for certain whether the geysers have anything to do with the ocean in Europa's interior, or they come from gargantuan lakes embedded in the satellite's icy crust. Today, the composition of the subsurface ocean on the satellite is estimated by analyzing the ice covering the inner part of its largest craters. Only a really large object is capable of breaking the thick layer of the ice clean through on impact. After the icy crust is broken, the water in the subsurface ocean at the impact site freezes and forms the bottom of a crater. Spectral analysis of the craters reveals magnesium, sulfur and iron compounds, as well as hydrogen peroxide and strong acids. This demonstrates that there is a vast diversity of minerals in the satellite's concealed hydrosphere. Europa's atmosphere contains oxygen, which forms as a result of ultraviolet radiation interacting with the ice water on the surface, splitting the water into oxygen and hydrogen. The satellite's atmosphere, however, is approximately 1 trillion times as rarefied as that of our Earth. Still, according to some estimates, concentration of oxygen in Europa's subsurface ocean should be sufficient for supporting single-cell aerobic life forms. Underwater volcanoes should be their sources of energy and food, as they saturate water with sulfur and iron oxides. Primitive organisms may attach themselves to the bottom side of the ice crust or swim freely in water. It was even assumed that there may dwell primitive multicellular organisms in Europa's ocean. However, this hypothesis appears to be rather too presumptuous. In fact, there is a great many species on our Earth which would be able to survive in the estimated conditions of Europa's subsurface ocean. There are among them not only bacteria resistant to harsh environments, but multicellular creatures too. For example, tardigrades. Consequently, we cannot rule out the possibility of primitive life originating in the depths of this celestial object of its own accord. Unfortunately enough, in spite of the keen interest we have in Jupiter and its satellites, so far they have been investigated only briefly, and that by spacecraft passing them on their way elsewhere. No landings on the gas giant's satellites have so far been attempted. At the moment, the largest planet in our system is being investigated by the Juno probe, but as soon as in July 2021, it will move on to studying the Galilean moons. The data collected by Juno will undoubtedly be of great importance and help get to the bottom of processes taking place in Jupiter's system. As for upcoming missions, back in 2012, the European Space Agency announced starting work on the JUICE project, or Jupiter Icy Moon Explorer. The mission of the project is to explore in detail the gas giant itself, as well as Ganymede, Europa and Callisto. JUICE will be launched next year, but will reach Jupiter's environs only in 2029. The mission is scheduled until the year 2033. If all goes according to plan, our knowledge about the gas giant and its satellites will be substantially expanded. Another big research project is NASA's Europa Clipper. This automatic probe is planned to lift off the Earth's surface not later than 2023 and to reach Jupiter's system in 2032. The probe's objective is quite predictably Europa. In contrast to JUICE, it is this celestial body that Clipper is supposed to focus on more closely. Today, over 300,000 small celestial bodies found here have been given names and numerical designations. Interestingly, their overall number may well reach over 1 million. The starting point of studying the asteroid belt may be defined at 1801, when astronomers spotted a mysterious object in the sky after a long and hard search for the fifth planet. In terms of its parameters, it appeared to be a planet, but happened to be so small that even the most advanced telescopes of the day couldn't distinguish its disk. The researchers saw the newly discovered object as a bright dot like a star. It was dubbed Ceres, and very soon similar celestial objects of this class were discovered. A new term had to be introduced to refer to them. These unusual astronomical bodies came to be called asteroids, which literally means star-like. Apart from asteroids, this area in the solar system contains great amounts of cosmic dust. While slowly spiraling up, its tiny particles scatter sun rays and create a very faint white glow. This glow is referred to as zodiacal light. Interestingly, in equatorial areas of the Earth, it can be seen with the naked eye. For a long time, the following hypothesis used to be widely accepted. Asteroid belt objects were thought to be debris of a destroyed planet. However, today this assumption doesn't really hold water. First of all, the mass total of all the objects of the main asteroid belt is too small and equals just 3 times 10 to the power of 21 kilograms, or 4% the mass of the Moon. Even allowing for the fact that the greater part of asteroids would have left the belt a while ago, the total mass of the rocky debris still falls short of making up an object with dimensions comparable to those of a proper planet. Secondly, estimates show that large celestial objects cannot form in this area of the solar system on account of Jupiter's gravitational influence. Mathematical modeling revealed that the largest formations in the asteroid belt have never measured over 1,000 kilometers in diameter. The gravitational influence of their mighty giant neighbor rendered their orbits highly unstable, which made potential protoplanets collide and disintegrate into smaller bits. Traces of these collisions can still be observed. Most objects of the main belt group together to form the so-called asteroid families, populations of asteroids of similar makeup and of the same origin. It is thought that they formed as a result of such destructive collisions. The borders of the main asteroid belt are rather blurred. Most of the objects making it up lie within 2.06 to 3.27 astronomical units from the Sun. These boundaries are predefined by Jupiter's tidal forces and are referred to as Kirkwood gaps. Any celestial objects getting into these zones experience the massive gas giant's strong gravitational influence, which destabilizes their orbits. This is the reason why the space object count here is considerably lower than beyond. Kirkwood gaps can be found not only on the conventional borders of the belt, but inside it too. Two of the most clearly defined gaps lie 2.5 and 2.82 astronomical units away from the Sun. The asteroid belt is also conventionally divided into 2 large areas, inner and outer belt. The border between them is a Kirkwood gap with a radius measuring 2.5 astronomical units, which coincides with the highest orbital resonance with Jupiter. It's in the outer part of the main belt that the largest object in this area of the solar system is situated, Ceres. This celestial object used to be thought a planet, then an asteroid, but eventually in 2006 it was given the status of a dwarf planet. It was possible to do so thanks to the fact that Ceres has a spherical shape, unlike the absolute majority of the other objects in the belt. Its diameter measures around 940 kilometers and its mass 9.4 times 10 to the power of 20 kilograms, which incidentally accounts for around a third of the overall mass of the asteroid belt. This makes Ceres approximately 6,000 times lighter than our planet. The furthest point of the dwarf planet's orbit from the Sun is 2.9 astronomical units. When Ceres is at its perihelion, the distance to our system's center measures around 2.5 astronomical units. At this point, the planetoid's surface temperature may reach 239 Kelvin or 33 degrees Celsius below zero, although its average temperature is noticeably smaller, at just 167 Kelvin or 106 degrees Celsius below zero. The celestial body is thought to be made up of a rocky core enveloped in a cryomantle around 100 kilometers thick. Water ice accounts for up to a half of the dwarf planet's volume, or 20 to 30% of its mass. The inner part of the belt harbors the largest and most massive known asteroid in the solar system, Vesta. The object's average diameter measures roughly 525 kilometers, and its mass is around 2.6 times 10 to the power of 20 kilograms, which is almost 4 times as little as that of Ceres. The asteroid's orbit is rather elongated, with its aphelion 2.57 astronomical units and its perihelion around 2.15 astronomical units away. It takes the celestial body 3.6 Earth years to complete a full orbit around the Sun. Vesta is also remarkable for being the only asteroid visible to the naked eye. It can be seen not only on account of its impressive dimensions, but also thanks to its comparatively light surface that reflects about 42% of light shed on it. Besides, the minimal distance between Vesta and the Earth isn't that great, at just 177 million kilometers or 1.18 astronomical units. It is assumed that Vesta is a fully fledged planet in terms of its inner makeup. It appears to have a metallic core made up of nickel and iron, as well as a rocky mantle. The surface temperature of the asteroid is currently fluctuating between -190 and -20 degrees Celsius, but it used to be much warmer in the past. Dark areas to be seen on the surface in the Western Hemisphere are highly likely to be basalt plains. Such terrain features may have formed as a result of volcanic activity or collision events with massive astronomical bodies. The most outstanding geological feature on the asteroid is the giant impact crater referred to as Rhea Silvia, whose diameter measures up to 500 kilometers, and its depth is around 25,000 meters. The second largest mountain in the solar system is situated at its center, towering higher than 22 kilometers. Impressively, the crater's diameter almost equals Vesta's size. It looks like the asteroid collided with a really large object at some point in the past. The collision would have produced not only the Rhea Silvia crater, but also a great number of small bits, which are now classified as the family of Vesta's numerous asteroids. The family counts over 15,000 objects, making up around 5% of all celestial bodies of the main belt known to science today. It is posited that most asteroid families came to be as a result of destructive collisions of two large celestial objects. Sometimes the debris are mutually attracted by gravity forces, which usually blend them into a new astronomical object. However, it would have lost its monolithic nature, and sometimes astronomers informally call such formations rubble piles. For example, Sylvia, one of the largest objects in the asteroid belt, seems to fall into this category of celestial bodies. Its parameters are 384 by 262 by 232 kilometers, with a mass 1.5 times 10 to the power of 19 kilograms. This makes the asteroid's average density just 20% higher than that of water. Estimates show that cavities may account for 25 to 60% of its volume. It takes Sylvia 6.5 years to complete a full orbit around the Sun. The object's orbit's furthest point from the center of the system is up to 3.7 astronomical units. In its perihelion, Sylvia gets as close to the Sun as 3.2 astronomical units. It is assumed that some bits of debris left after a collision are not attracted to other bits but rather become satellites of the new celestial body. Sylvia is known to have two such companions, Romulus, with a diameter measuring 18 kilometers, and Remus, measuring around 7 kilometers. Their makeup hasn't been studied yet, and it is highly likely that these objects are not monolithic either. Besides, Sylvia may theoretically have smaller satellites as well, which haven't been detected yet. Pallas is another remarkable object in the asteroid belt. It was discovered back in 1802 right after Ceres, and is the second largest asteroid in the belt. The average diameter of the celestial body is around 512 kilometers, and its mass is roughly 2 times 10 to the power of 20 kilograms, which is approximately 25% less than that of Vesta. The asteroid's orbit is exceptionally elongated and tilts to the ecliptic plane at 35 degrees. That is the reason why the astronomical body is so hard to investigate with probes. As for its orbital period, it takes Pallas around 4.6 years to orbit the Sun, in the course of which the distance to the system's center changes more than 1.5 times. With its perihelion 2.1 astronomical units, its aphelion is 3.4 astronomical units away. Pallas's surface is widely pockmarked with craters, much more so than the larger Ceres or Vesta. Studies of the chemical composition of the asteroid's surface reveal that it mostly consists of silicate rocks with small amounts of iron and water. Just like Vesta, this celestial body is thought to be one of the few potential protoplanets that are still around, which means that studying it may yield important information about the formation process of the solar system. Unlike Vesta, most asteroids cannot be seen either with the naked eye or through amateur telescopes. One of these elusive objects is called Interamnia, admittedly one of the most mysterious objects of the main asteroid belt. This is an irregular-shaped asteroid with parameters 362 by 348 by 310 kilometers, and its mass accounts for roughly 1.2% of the overall mass of all objects in the belt. In spite of its relatively large size, however, Interamnia remains largely understudied. One of the difficulties thwarting scientific progress here is the asteroid's dark surface, which absorbs around 93% of light shed on it. Interamnia falls into the exceptionally rare spectral class F, which is a subclass of carbonaceous asteroids. Research of its reflection shows that the color of the celestial body's surface is even, which means that Interamnia hasn't experienced big collisions for quite a long time. Interamnia's density is not that great, at just twice that of water. The asteroid is thought to be made up of a hard rocky core enveloped in a thick layer of ice. The surface is covered with great amounts of fine dark dust. It takes Interamnia around 5 years and 4 months to complete a full orbit around the Sun. Its aphelion is on the opposite side from 4 largest objects of the main belt, and the distance from the asteroid to the Sun varies from 2.5 to 3.5 astronomical units. In theory, Interamnia's orbit crosses the trajectories of such large objects as Ceres and Pallas, but estimates show that chances of their colliding with each other are small. There are millions of objects in the main belt, from dwarf planets to tiny meteoroids the size of a cobblestone. However, distances between them measure thousands upon thousands or even millions of kilometers. That is why a spacecraft crossing the belt would be running an almost negligible risk of getting hit by any astronomical body. Still, mathematical modeling shows that around once every 10 million years, some remarkable collisions take place in this part of the solar system that produce new debris. Even though a manned mission to asteroids in the main belt will not be in the pipeline for a long while, some of the asteroids there have been studied with the help of interplanetary space probes. For example, the Dawn probe carried out observations of Ceres and Vesta in the period from 2011 to 2016. Quite recently, the space probe Lucy blasted off the surface of the Earth. Even though its main goal is the so-called Jupiter Trojans, the spacecraft will approach the object known as Donald Johanson in the main belt and take its pictures in 2025. Also, the launch of the Psyche project is scheduled for July 2022, with the largest known metallic asteroid of the main belt as its target. Within the mission, the probe is planned to reach its destination by early 2026 and remain in the asteroid belt for at least 21 months while studying the asteroid's terrain, makeup, and magnetic field. One flap of a butterfly's wing in Brazil would be enough to cause a hurricane in Indonesia. Edward Norton Lorenz. 1893. Kyoto, Japan. Young lawyer Henry Stimson and his wife Mabel White are on their honeymoon in Kyoto. The newlyweds are stunned by the colorful oriental city and its ancient history. They will remember this visit for the rest of their lives. May 11, 1945, Los Alamos, USA. A special U.S. Army committee makes a list of priority targets for atomic bombings. Kyoto is top on the list as the largest industrial center in Japan. Pointing to the city's large cultural significance, the Minister of Defense Henry Stimson crosses it out from the list personally. This makes Hiroshima the main target for the US Army. Next in line at risk of bombing is the town of Kokura. August 9th, 1945, Japan. The crew of the US Air Force B-29 bomber is given a specially important order by the commanders. The military arsenal in Kokura must be razed to the ground. A state-of-the-art bomb, more powerful than any used before, is loaded on board the aircraft for the mission. However, the town is enveloped in a fog so thick that the crew cannot distinguish the target. The aircraft captain Charles Sweeney takes a decision to fly on, to the town of Nagasaki. Thus, some sentimental reminiscences of 50 years back and an ordinary weather event affected the destinies of millions of people. And this story is just one of a great multitude of examples where seemingly small events may give rise to major consequences, incredible in their scale. This phenomenon is commonly perceived as the butterfly effect. But in reality, it is actually just a part of a big field of science known as chaos theory. In order to have a clearer insight into the correlation between small arthropods and destructive weather events, let's travel back to the recent past. In 1961, mathematician and meteorologist Edward Lorenz attempted to forecast the behavior of atmospheric flows by means of computer modeling. The scientist assumed that thanks to new computing capabilities, he would be able to predict the weather with an unprecedented accuracy. However, the results of the calculations baffled the scientist. In order to try to speed up the calculation process, Lorenz divided it into stages, so that the final results of the previous stage would be the starting conditions for the one coming next. Some of the resulting figures were slightly rounded up by the computer. This was so negligible that it was not supposed to have any significant impact on the final answer. Or so the scientist thought. However, in reality it turned out that the results of uninterrupted and stage-by-stage calculations differed dramatically. Later studies revealed that the system of equations Lorenz was trying to solve was inadequate for atmospheric processes modeling. Still, as is often the case in science, a misformulated task proved to be a step to an amazing and unexpected discovery. In his search for answers, the mathematician found that all possible solutions of the system group around two conventional positions which he dubbed attractors. If every solution were to be represented by a dot in a 3D coordinate system, they eventually form a shape reminiscent of a butterfly's wings. Interestingly, the slightest change of any initial parameter may sharply transfer the final calculation result from one wing to the other. In fact, Lorentz was not the first to discover an effect like that. Similar ideas were expressed by German philosopher Johann Fichte and French mathematician Henri Poincaré in their works. Be it as it may, it was Lorentz who transformed the annoying error of mathematical modeling into a potent and elaborate theory capable of offering answers to many questions. It goes without saying that hundreds of scientists would have contributed to the notion of chaos in the decades that followed, and the theory itself has come a long way. Its mechanisms can be applied to describe such complex phenomena and processes as turbulent flows, evolution of biological species, social interactions, and stock exchange quotes. The laws of chaos define the movement of celestial objects and explosions of stars, the birth of empires, and the demise of continents. And in order to get to the bottom of these factors and regularities, first and foremost, the notion of chaos has to be defined from the point of view of science. First of all, it should be noted that any chaotic structure is subject to rather rigid and clear physical laws, but they are so complex that the behavior of a system appears to be unpredictable. It is for a reason that structures like that are also known as deterministic chaos, with reference to their behavior being predefined. This is the principal feature that distinguishes them from stochastic systems, which are based on truly random events. If a chaotic system's behavior is supervised several times, the initial conditions being absolutely identical, it will react in the same manner. As for a structure based on pure chance, meanwhile, the result will never be the same. For example, experiments show that the decay of unstable nuclei in a sample of radioactive material occurs exclusively by chance. We can calculate the approximate number of atoms transforming within a specified period of time, but at the current stage of technological development, it is impossible to predict the precise time a given nucleus is supposed to decay. The exact mathematical definition of chaos sounds like this. A system has to exhibit nonlinear characteristics, be globally stable, but at the same time have at least one oscillating equilibrium point. At the same time, the system's fractal dimension must not be less than 1.5. It's quite a challenge to get one's head around this convoluted phrase, unless one is a professional mathematician, of course, rather than a layman. In simple words, it may be expressed by three principal points. Firstly, the system has to be nonlinear. Let's imagine we're influencing a structure in one way or another and getting a predictable feedback. It is logical to assume that after several interactions of this kind, the resulting change will equal the sum of all single ones. However, it isn't the case for a nonlinear system, and as a result, the structure will change more or less than we estimated. This was the effect encountered by Lorentz in his calculations, which prompted him to carry on with his studies. Secondly, a dynamic chaos system must be responsive to the initial conditions, that is, to exhibit this very butterfly effect. This means that no matter how tiny and almost completely negligible change of the initial conditions may be, it may force the system to develop in a completely different manner. Thirdly, as a system develops, its separate parts are supposed to overlap and interact with each other. Such interactions are usually not taken into account in classical physics. However, quite often it proves to be a grave omission. It is keeping track of multifaceted influence that makes chaos theory models so elaborate and so like real structures. Let's think 13.8 billion years back. Just a few quanta of time would have elapsed since the occurrence of the hypothetical Big Bang. There is neither matter nor energy around us as we know them, and the four fundamental interactions are interconnected by one bizarre force. The physical laws known to us are not yet applicable at this point. However, other ones are working instead. which are just as rigid and which predefine the system's future development. At the same time, a tiniest change in any point of the germinating universe is capable of changing its future completely, whatever the reason for this tiny change. It appears that our reality was literally born actually thanks to chaos, in the scientific sense of the word. Now let's imagine what it's like about 1 million years later. The space of that time would have become more like what we know it to be. Although there aren't any stars or planets around, there are only countless clouds of primary hydrogen floating around the young universe. The hydrogen is exposed to gravity forces pressure. This forms gravity centers which are soon to become the first stars. These gas clusters are splashed about quite irregularly, with no system to speak of. They are also massive enough to mutually exert gravitational influence. At the same time, with any of the protostars moved aside, or with its mass slightly altered, these changes will influence not only its own evolution, but that of its immediate neighbors as well. This means that the laws of chaos continue to rule the universe. In the course of billions of years that followed, primary stars burned out and exploded, saturating the universe with heavy elements. New stars were born from clusters of hydrogen, with clouds of cosmic dust near them swirling in gigantic vortices and forming protoplanetary disks. It is easy to see the already familiar patterns of chaotic movement and interaction in their structure. And this is how 4.5 billion years ago the solar system was born. The outer part of the solar system is still largely understudied and full of mysteries. Spacecraft have already brought us a wealth of knowledge about the giant planets and their satellites, but much of the information remains uninterpreted. Despite all difficulties, the process of cognition never stops, which means that there are yet more discoveries lying ahead. And let's keep in touch.